Have you ever looked at a wall and thought, "That's solid, I can't walk through it"? Well, what if I told you that at a tiny, invisible level, the universe plays by a completely different set of rules? Rules so strange they sound like science fiction, but they're actually the foundation of everything you see. Welcome to the world of quantum physics. So, what is quantum physics? Simply put, it's the science of the very, very small. We're talking about atoms, electrons, photons of light. The fundamental building blocks of reality. The physics we learned in school, like a ball flying through the air, that's called classical physics. And it works perfectly for big things. But when you zoom way down to the atomic scale, those rules break down completely. It's like discovering that chess pieces move differently when no one is looking. Let's dive into one of the weirdest ideas first: wave-particle duality. Imagine an electron. Is it a tiny solid ball, or is it a wave, spread out like a ripple in a pond? The quantum answer is yes, it's both at the same time. The most famous demonstration of this is the double-slit experiment. If you shoot tiny particles, like electrons, at a wall with two slits in it, you'd expect to see two lines on the screen behind it, right? Like spray painting through a stencil. But that's not what happens. Instead, you get a pattern of many lines, an interference pattern, which is something only waves do when they overlap. It's as if each single electron goes through both slits at once, as a wave, and interferes with itself. But here's where it gets even stranger. If you place a detector at the slits to see which one the electron goes through, the wave pattern vanishes. Suddenly, you get just two lines, as if the electron started behaving like normal little balls. The very act of observing it changes its behavior. This is called the measurement problem, and it suggests that reality itself is somehow influenced by whether or not we're looking. This leads us to another core concept: superposition. This is the idea that a particle can be in multiple states at once until it's measured. Think of a spinning coin. While it's in the air, it's not heads or tails. It's a blur of both possibilities. Only when it lands and you look at it does it choose a state. A quantum particle is like that spinning coin. An electron can be in multiple locations or have multiple energy levels all at the same time. This isn't just a quirky idea, it's the powerhouse behind quantum computing. A regular computer bit is either a 0 or a 1. A quantum bit or qubit can be a 0 or 1, or both simultaneously, allowing it to process an incredible amount of information. Next up is what Einstein famously called spooky action at a distance: quantum entanglement. You can link two particles together in a special way so that they share the same fate, no matter how far apart they are. Imagine you have two of these entangled particles. If one spins clockwise, you will instantly know the other is spinning counterclockwise, even if it's on the other side of the galaxy. Measuring one immediately affects the other faster than the speed of light. Experiments have proven this is real, challenging our deepest intuitions about space and time. It's as if the universe has a secret, invisible connection between these particles. So how can all this be? A lot of it comes down to the uncertainty principle, formulated by Werner Heisenberg. It states that there's a fundamental limit to what we can know about a particle. Specifically, you can't know both its exact position and its exact momentum, or speed, at the same time. The more precisely you measure its position, the less you know about its speed, and vice versa. This isn't because our tools aren't good enough. It's a built-in feature of nature. It's this inherent fuzziness that allows for all the other strange quantum effects. One of the most mind-bending consequences of this uncertainty is quantum tunneling. Because a particle's position is uncertain, it has a small but real probability of appearing on the other side of a barrier it should not be able to cross. It's like throwing a tennis ball at a wall, and instead of bouncing back, it just appears on the other side. This sounds impossible, but it's happening constantly. Quantum tunneling is the reason our sun shines. The pressure at the sun's core isn't high enough for atoms to fuse together classically. But thanks to tunneling, they can overcome their repulsion and merge, releasing enormous energy. It's also used in modern electronics, like flash memory in your smartphone. And that brings us to a crucial point. Quantum physics isn't some abstract theory with no real-world impact. It is the foundation of our modern world. Your smartphone, the lasers in a barcode scanner, MRI machines in hospitals, the GPS that guides you. All of these technologies only work because we understand and harness quantum mechanics. It's the basis of all chemistry. explaining how atoms bond to form molecules and why materials have the properties they do. Underneath the solid, predictable world we see, there is a buzzing, probabilistic quantum reality that makes it all possible. So, what's next? The future is quantum. Quantum computers, leveraging superposition and entanglement, promise to solve problems that are impossible for even the most powerful supercomputers today. Imagine designing new medicines molecule by molecule, creating new materials with incredible properties, developing unbreakable encryption, or revolutionizing artificial intelligence. These aren't just dreams. Labs around the world are racing to build functional quantum machines that will transform science and technology as we know it. So why does the quantum world feel so weird and counterintuitive? The answer is simple. Our brains didn't evolve to understand it. We evolved in a world of big, slow-moving objects, where things have definite locations and predictable paths. Our intuition is built for the classical world, but the quantum realm isn't weird. It just follows different rules, and those rules are consistent, logical, and in their own way, incredibly beautiful. It's a reminder that there's always a deeper layer to reality waiting to be discovered. The universe is far stranger and more wonderful than we can imagine. Thanks for joining me on this journey into the quantum world. If you enjoyed this and want to explore more of the mysteries of science, be sure to like, subscribe, and hit that notification bell. Until next time, stay curious.